Hello students, we shall go ahead with the next topic in molecular spectroscopy. That is, we are going to go ahead with the continuation in rotational spectrum. In today's class, we are going to study regarding the spectral intensity, distribution using population distribution, that is Maxwell-Boltzmann distribution, determination of bond length. So in today's class, we are going to study regarding spectral intensity, distribution using population distribution, that is Maxwell-Boltzmann distribution, and finally the determination of bond length. Coming to the spectral intensity. In case of rotational spectrum, all lines are not equally intense. In case of rotational spectrum, all lines are not equally intense. Intensity depends on transition probability and concentration or path length. When I tell transition probability, that is the number of atoms or molecules initially in the state from which transition occurs, that is the population. So intensity depends upon the transition probability, that is the number of atoms or molecules initially in the state from which transition occurs, that is population. And next, when we were telling concentration or path length, the amount of material present giving rise to the spectrum, that is the amount of material present giving rise to the spectrum. For rotational spectra, the transition probabilities for various transitions are identical. For rotational spectra, the transition probabilities for various transitions are identical. That is, the line intensities will be directly proportional to the initial number of molecules in each level. That is, the line intensities is directly proportional to the initial number of molecules in each level. The population increases with increase in rotational number, attains a maximum value and then decreases. The population increases with increase in rotational number, attains a maximum and then decreases. The maximum population observed at J, that is the rotational number, is equal to under root kT by 2 hcb minus 1 by 2, where k is going to be the Boltzmann constant, T is going to be the temperature, H is going to be the Planck's constant, C is the velocity and B is the rotational constant. Transition between levels with very low or very high J values. Transition between very low and very high J values will have small intensities. That is, when there is going to be a transition between levels with very low or very high J values, will have small intensities, while the intensities will be maximum at or near the J where this equation is given. The intensity is maximum where J is given by this expression under root kT by 2 hcb minus 1 by 2. Now coming to the population distribution, that is Maxwell-Boltzmann distribution. When we are going to deal with population distribution, we are going to consider the Maxwell-Boltzmann distribution. Now, suppose n number of molecules are distributed between two different energy states. If n number of molecules are distributed between two different energy states, that is at a lower energy level and at upper energy level, and most of the molecules are going to occupy the lower state. Supposing we are going to tell, let most of the molecules occupy the lower state, then at equilibrium, the number of molecules, the ratio of the number of molecules in the upper state by the number of molecules in the lower state is given as, or n upper by n lower is equal to exponential minus delta E by kT. I can number this as equation 1, where T is the temperature, K is the Boltzmann constant and its value is equal to 1.38 into 10 raised to minus 23 joule per Kelvin. It is a Boltzmann constant, and delta E is going to be the difference in energy, that is from E upper minus E lower. If molecules transfer from J is equal to 0 to J is equal to J, that is, there is going to be a transfer of molecules from 0 to J, then the above expression becomes Nj by N0, that is from upper to lower one, is equal to exponential minus Ej by Kt, and this is equal to exponential minus Bhc J into J plus 1 by Kt, and this equation let me number as 2. So when I am going to plot a graph, that is between the J values, and exponential Bj into J plus 1 by into Hc by Kt, I am going to get a graph as such. When I go on to plot a graph between what? Increase in J values and the exponential one, this is going to be the graph which we are going to get. Although the molecular population in each level decreases, although the molecular population in each level decreases exponentially, there is going to be a decrease in the population exponentially, the number of degenerate levels available increases rapidly with J. That is, with increase in J, the degenerate levels available are going to increase. The total relative population at an energy Ej will be given, that is, population is proportional to 2J plus 1 exponential minus Ej by Kt, and this is equation 3. Now when I am going to plot between J values with increase in J and with the exponential, that is going to be exponential Ej, that is B into J into J plus 1 Hc by Kt. When I go on to plot this against J, I go on to get a maxima, and then there is going to be an exponential decrease. So what do we observe here is, when this expression 3 is going to be differentiated, it shows that the population is maximum. When this expression is going to be differentiated, it shows that the population is maximum at the nearest integral J, where the population is going to be maximum when J is equal to under root Kt by 2 Hcb minus 1 by 2. So there is going to be, that is at this case the population is going to be maximum. That is, at this case the expression is going to be given as J is equal to under root Kt by 2 Hcb minus 1 by 2. This was regarding the Maxwell-Boltzmann distribution of the population when they are, that is the molecules when they are going to get excited or get transition from one energy level to another energy level. And the last part of today's class is going to be determination of bond length. The last part in today's class is going to be determination of bond length. The rotational spectrum data can successfully be used to calculate bond length of a diatomic molecule. The rotational spectrum data can be used to calculate the bond length of diatomic molecules. Molecules such as HCl, carbon monoxide, etc. will show rotational spectrum because there is going to be a change in dipole moment, while N2 and O2 will not show. That is, molecules like HCl and carbon monoxide will show rotational spectrum because there is going to be a change in dipole moment, whereas N2 and O2 will not show. The line spacing between delta J is equal to plus or minus 1 we had seen in the last class to be as 2b. In rotational spectra, the line spacing is going to be 2b, and b can be calculated. The value of b can be calculated. The value of b is used. To calculate the moment of inertia, because I can calculate this from the spectra because The spacing is going to give me 2b, and b I can calculate. Once I know the value of b, I can calculate the moment of inertia using the expression I is equal to h by 8 pi square bc. I know b and I know c. I can calculate moment of inertia. And I know moment of inertia is related to bond length as I is equal to mu r square. I is equal to mu r square, and I know mu is equal to reduced mass, and mathematically it is given as m1 m2 by m1 plus m2. So if I know the atomic masses of the two atoms, I can calculate the reduced mass. Once I know the reduced mass, what happens? The expression is going to be r square will be equal to I by mu, or r will be equal to under root I by mu. And thus I can determine the bond length of a diatomic molecule. So in today's class we had seen the spectral intensity, the population distribution, that is Maxwell Boltzmann distribution, and the determination of bond length. Thank you.